In the last lesson, we introduced the concept of gradient descent, which minimizes the error at every iteration, constantly giving us a better linear model that better classifies our data, until we obtain the perfect model. We introduced the equation, which is simply the derivative of the error function with respect to its weights. Before implementing gradient descent onto our code, there's some things we need to fix. First and foremost, let's delete the line that we hard-coded early on. It's the computer's job to determine the line that best classifies our data, not ours. We're not going to be hard coding it. That said, we'll just set the initial linear parameters equal to all zeros. Line parameters equal to np.matrix, and inside of it, we'll just declare an array of zeros. And there will be 3 of them. This will simply have weights and bias values of zeros, which will end up being a horizontal line at the origin. And what we'll do actually is comment out these lines as well and get rid of that one. Alright, now we're off to a fresh start. Back upstairs, we will declare a function, def gradient descent, which takes in the line parameters, all of our points, the labels, a learning rate variable, which I'm just going to call alpha. And inside the function, we'll start with a for loop, for I in range of 500. We're going to have 500 iterations to fix our line and minimize the error. And at each iteration, we'll calculate the gradient of the current error. Recall that the gradient of a linear model's error function is obtained by the following equation. Following this, we'll set gradient is equal to points. And it looks like we have to multiply it by the sigmoid of the probability of each point in the graph. So let's set p is equal to sigmoid points times line parameters. Let's get rid of these print statements. And so we'll multiply this by the sigmoid. And according to the function, we have to minus the labels first, minus y. These are both 20 by 1 arrays, so subtracting them from each other will result in a 20 by 1 array. This here is a 20 by 3 array. For matrix multiplication between these two to occur, the same number of columns here needs to equal the same number of rows here. So we'll take its transpose. That way we get a 3 by 20 array, which is compatible with the dimensions of the 20 by 1 matrix. We have to now divide by m the number of points, or in this case the number of rows in our points array. We obtained the number of rows previously over here, so let's just copy and paste that over right here and multiply everything by 1 over m. And that is the gradient. Subtracting this value from our linear parameters results in new updated weights for a new line, which will thereby have a smaller error function than the previous. So what we'll do is update our line parameters variable and set it equal to line parameters, I'll just copy and paste it, it's pretty long, minus the gradient. And remember, one thing we have to do is we want to take very small leaps from one line to the other. We don't want the value of our lines to change drastically in each iteration. We know that subtracting the gradient adjusts the weights of the line in the direction which gives us the least error. We don't want it to move too far in that direction, so we'll scale our gradient down by multiplying everything with a learning rate, which we're later going to specify as a very small value. It is named alpha. This ensures that we're still going in the direction that best minimizes the error, but we're doing it in small steps. Alright, now based on the linear parameters, we'll set the coordinates for a new line by simply copying and pasting what we had previously. Instead of bottom region and top region, let's just index the entire array of points. We will get the same results. And as for here, the bias and the weights we can access from line parameters. But if you were to print this value, you would realize that W1 is the first item, W2 is the second, and the bias value is the third. So what we'll do is we will write W1 is equal to line parameters dot item 0. We'll copy that for W2 and for B. Except W2 is in item number 2 and B is item number 3, which is at index 2. And believe it or not, we're done. At every single iteration, we minimize the error of some line by subtracting the gradient of the error, obtaining a new line with a smaller error, and we keep doing that over and over 500 times. Finally, after the for loop, we will draw the line with the smallest error by simply calling draw x1 and x2, and instead of 10 points, we will switch this to 100 points on each side. And let's now call the function gradient descent, passing in the proper arguments, line parameters, all points. I believe the third argument are the labels, and a small learning rate alpha of, let's say, 0.06, something small. We'll run our code. And there is the line that best classifies our data. But clearly I forgot to run the cell, which switches this to 100 points. All right, there's our line. If instead of 500 iterations, I do 2,000 iterations, notice that we get a much better line. Since the more you increase the number of iterations, the more it minimizes the error, and thus the better your line is in classifying your data. If you want to see a visual of how the line updates itself at each iteration in the for loop before it comes up with this line, let's actually merge all of these cells. First, let's select all of them with Command A or Control A if you're using a PC, and we will click on Shift M to merge all of our cells. Copy and paste all of this code inside of a new Atom project. We will copy this. And let's add some animations. Since we're drawing 2,000 lines, we want to make sure that whenever we draw a line, we remove the old one, the first line. That is, the line at index 0, we will remove it and only have the new one. Update our plots. And since we're dealing with a line that's actively being updated and displayed, we need to call plt.pause 0.0001 seconds. In every update, this pauses the figure in 0.001 second intervals. Alright, and finally, instead of drawing our line after the for loop, we will draw every single line in the loop. Finally, let's just run the code in our terminal, cd desktop, cd logistic regression. That is my project name. And what we'll do is run python logistic.py. And there you go. It started off with a random line at 0, 0, 0, and it uses gradient descent to minimize the error at each iteration, and thus obtaining a new linear model that better classifies our data every single time. To actually stop this, since we're not going to wait 2,000 iterations, what you can do is press Ctrl+C, and inside of the gradient descent function, we'll actually print the error of every single line that's being updated. So we'll just print calculate error, line parameters, points, and y. Rerun the code. Seems we have an extra print statement that we need to get rid of. Let's actually stop this and get rid of the extra tenuous print statements. This one can go back here. And check it out, the error gets smaller every time the line fixes itself. This is further confirmation that gradient descent is doing its job pretty well.